Welcome back. We're going to talk now about how we would analyze the merge sort algorithm, which, as you recall, is a recursive algorithm. And so standard analysis tools fall apart a little bit, at least the ones that we've talked about so far. As a reminder, here's the recursive portion of merge sort. We have our base case. If left and right are the same, or for some reason right is less than left, then we do nothing because we have an array that's length 1 or 0. But if the arrays of length 2 or greater, then we do the recursive portion, which is we calculate the center, we merge sort the left portion, we merge sort the right portion, and then we merge those two portions together. And since these two are these two calls are to the function itself, this is the recursive part. Okay. Now, in order to analyze this, we need to take this recursive structure into account when we do our analysis. Now, we can write down some basic facts. And the first basic fact we know is that if you have an array of length 1, then the time to sort that is on the order of 1. So I could write this as t of 1 equals 1 or t of 1 equals big O of 1. Okay? What does that mean? This is simply saying that if you have an array of length 1, it takes a constant amount of time to sort that array. Nothing too complicated here. But this is our base case because we stop our recursion when we get to an array of length 1. Now, the more interesting thing is the recursive portion. We don't know what the running time for the recursive portion is, but we can write it down in a recursive manner itself. So in other words, we can write down t of n in terms of itself. And so that's what we have written down here. I've written down t of n equals 2 times t of n over 2 plus big O of n. Okay, where does this come from? Well, the 2 times, this 2 comes from the fact that each time we're recursing twice on the left portion and the right portion. And when we recurse, we're recursing on an array of size half of what we were given. So the left portion is half as big, the right portion is half as big. So we're doing 2 times the work that we would do for an array that's half that length. And then where does this big O of n come from? Well, that comes from the merge itself at the end of the recursion, after we've done all the recursion. So we have a recursive description of the runtime, but this is not a closed form solution. In other words, maybe you could figure this out if you plugged in a particular n, but this doesn't give us something like t of n equals big O of n squared or n log n, which is what we would like. We want a closed form solution which says, given an n, we can just directly calculate in a finite number of steps or a fixed number of steps what the runtime would be. So instead of doing this in the text window here, what I'm going to do is show you sort of a more mathematically inclined way of doing this, okay, or more a nicer looking slide here. Okay, so we've already written these two things down. We wrote down this t of 1 equals 1. That's our base case. We've also written this down. T of n is equal to 2 times t of n over 2 plus big O of n. And again, just so that we're clear, 2 times because we're doing 2 recursive calls. Each of those recursive calls is on an array of size n over 2, and the running time for each of those recursive calls is whatever the running time is for an array of that size. So in other words, again, this is a recursive definition of t of n. And then finally, the big O of n is the cost of merging the 2 arrays that we were given, the 2 subarrays that we just sorted. Okay, so this is our recursive case. That's what we had on the text window before. Now, I want to take this thing right here, okay, and rewrite it just by dividing everything in this recursive statement by n. So I'm going to divide by n, and what that's going to give me is this statement right here. Okay, t of n divided by n. Why? Well, because we're dividing everything by n. Why are we dividing everything by n? Well, you'll see. Once we come to collect our terms, we'll find out that this is useful. So we have 2 times t of n over 2 divided by n plus big O of 1. Now, where did the n go? Well, it's because we divided by n. And then finally, we're going to just move the 2 down. Which 2? We're going to move this 2 down into the denominator, and it goes here, and we're left with this. Okay? So we have t of n over n is equal to t of n over 2 divided by n over 2 plus big O of 1. That's where we begin our analysis of this recursive function. So if we scroll down a bit, we have that exact statement again. Okay, that's where we just were. T of n over n equals t of n over 2 plus n over 2 plus 1. Okay, well, if we knew what this was, then we would be happy because we would be able to just solve this directly for t of n. But we don't know what that is. But we do have a definition for t of n, a recursive definition. In fact, it's defined right here. And so we could take this and move it down here, right? And that is defined as, well, the time to run for an array of size n over 2 divided by n over 2 is exactly equal to this portion, t of n over 4 over n over 4 plus 1. Okay? And we get that just by pattern. How do we know that? Well, we get that just by pattern matching. If you replace n everywhere in this definition up here with n over 2, then you get this definition right here. Well, so if we were able to know what t of n over 4 over n over 4 was, we could plug it in here. We would get the answer to this. Then we would get the answer, which would be the answer to this, which we could plug in and get the answer for t of n. But we don't. But we could take this right here and use it to define t of n over 4 over n over 4, which is t of n over 8 over n over 8 plus 1, right? Don't forget that plus 1. It's important. And so on. We could continue redefining these terms in terms of smaller and smaller subarrays. And you say, well, when does this end? Why doesn't this just go on forever? Well, it doesn't go on forever because if we look down here, eventually this n over something, notice that the denominator is doubling every time we go down, right? 2, 4, 8, 16, 32. Eventually, we're going to get to something where we have essentially n divided by n, or something close to that, right? The denominator eventually is going to get so large that we're going to have t of n over n, which is 1 over 1 plus 1. And we know the definition of t of 1 over 1, that's just 1. And how do we know that? Well, because back up here, that's our base case, right? Right here. That's our base case. All right, so this might not look very good, but let's see what we can do with this. Let me sort of erase a few things here. Okay, and this, and this, and this, and this. All right, now, hopefully you agree that these things are equal, these things are equal, all these things are equal to each other. So if each of these terms on the left is equal to each of these definitions on the right, then you would also agree that if I were to do some sort of summation over all the terms that I'm circling here, if I can circle them carefully, there we go. If I were to add up all the terms that I just circled, since they're individually equal to each of the things on the right, then they would be, that sum would also be equal to everything on the left, I'm not sorry, on the right here. So again, a summation of everything on the left is equal to a summation of everything on the right, because every term on the left is equal to one of those terms on the right. If I were to do that, this is what's known as a telescoping sum. If I were to do that, you would notice that I would have on the left-hand side of this sum, or of this equal sign, I would have a sum that involves the term t of n over 2 over n over 2. But I have the same term over here. So guess what? I could cancel both of these terms. In other words, they cancel out. And the same goes for this, and the same goes for this, and so on. Okay, so almost everything would cancel out. Okay, and including this term, and this term. So what's left? Well, it turns out that what's left is just t of n over n, and on the right hand, that's the only thing that's left on the left hand side. And the only thing that's left on the right-hand side are all these ones. So those ones are important. So we get something like T of n over n is equal to 1 plus 1 plus dot 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 plus 1. Okay? And the question is, how many ones are there here? And the answer is, well, if you think about it, how many times could we double the denominator until we get down to n over n? Well, we can only double the denominator log of n times. So the number of ones that there are on the right-hand side here is log of n. So we have T of n over n is equal to log n. And that gives us T of n is equal to big O, in a big O sense, of n times log of n. And that's our analysis for merge sort, okay? As I said, this is a different type of analysis that used recursion and telescoping sums, which we haven't seen before, okay? So I wanted to show this to you. So let's go back and look at our comparison table for sorting analysis. Merge sort. What's the running time? Well, we just saw this is n log n. What's the big omega? It's also n log n because there's no short-circuiting all these recursive calls that we're making, okay? At least not in the code that we wrote. Is it a stable sorting algorithm? Well, we mentioned this in the previous lecture. Yes, it can be made stable. Does it operate in place? No, not easily. We have to have this extra buffer that we merge into and then copy back out of, okay? So that's merge sort. That's the analysis of merge sort. And I hope that clarifies for you why this is an n log n algorithm. Not only an elegant algorithm, but also a fast algorithm. Next time, we'll start talking about quicksort.